Okay, so welcome to the video on functions and subroutines for this introductory video to B07, our introduction to our using OR packages. So now we're going to look at functions further. As mentioned in the previous video, we're familiar with this idea of using a function of the mean of x, where you send x in as an argument to the function mean, and x might be a set of integers, and we can get the mean from that using this function. We could write out this function ourselves, but that would take a lot of time. So it's easier simply to use that function that exists already. Note that functions may or may not take in arguments and return data. Some send you back data, like you'll get the mean of x back from this. And some take in arguments like x here, x is an argument, but some don't. So what we can say is that a subroutine is a function that does not involve arguments nor returning data. So subroutine is a type of function. That's what you can say. So sometimes they're used interchangeably. Technically, that's not entirely true. So we pay attention to how we can use functions and subroutines appropriately. An example of how we can use inbuilt functions in R is when we're trying to do something like multiple test corrections. So if we test lots and lots of hypotheses, we may have a risk of having many false positives, and we don't want false positives. What we want to do is control our global error rate and reduce the rates of false positives so that we only look at the outcomes that are the most extreme in comparison to what we expect from random data. So one approach to this is simply to use a much lower p-value than the threshold, so the probability of getting any false positives is relatively lower. This is also known as the Bonferroni correction, which is simply the p-value of interest divided by the number of tests n that is completed. And we also remember that p-value is a function of the model used, the hypothesis being tested, and the probability of having a statistic observed or one and more extreme compared to a kind of null distribution. So the Bonferroni is not great, it's conservative. A more effective way for controlling the false discovery rate is to consider if your p-value of interest is more extreme than would be expected given its rank in the p-value distribution. And this links to the Benjamini-Hochberg method, which assumes that the p-value distribution is uniform. So if we ask this question, if we do 100 tests, say of genes, and we say our threshold is 0.05, what we're effectively saying is that I am going to have a bunch of p-values, and they're always going to be between 0 and 1. I'm going to say for each of the observations that we get here, what's the probability they're in the particular sequence after I sort them and rank them. So they should be in order, and you're asking, are they more extreme than the corresponding null p-value equivalent to that rank? So you move along our number line, but here we're focused mainly on the ones that are at the most extreme, below 0.05. So what we do is we rank our p-values. That fits this kind of number line here. We're ranking them, and we find that the largest rank such that the value of interest is less than or equal to this function. So it's the rank multiplied by 0.05, our p-value threshold, divided by 100. So if we have 100 tests here, what we're going to say is that I'm going to ask, is my p-value less than 0.0005 for the first one? This is our threshold. And if we've any set of 100 that we're testing, that will always be our threshold. If we observe that x1 is below that threshold, then we say, yes, this is extreme in this particular context. It might be worth further exploration. If x1 here is, for example, 0.006, we would in fact say no, and say this is not extreme, and we would reject all the remaining p-values. We say, actually, none of them are extreme here. It's not worth looking at further. However, in this case, we had a yes initially. So next we move on to our next rank, because we had yes initially. And we say, if this is less than 0.001, does it meet that criteria? For x2, we say, yes, that does. So note that x2 is actually above this original p-value, but for the second ranked p-value, it is still extreme. So you say, yes, this is extreme. It's worth further exploration in the context of everything else about this particular study. And then we move on further. So you can see the p-values actually are equidistant intervals. So next one's 0.0015, and here we have a value x3, our p-value is 0.0016. So we say, no, this is not extreme, and we skip the remainder. So note that. So that's how the Benjamini-Hochberg correction works. And what's nice is that you don't have to do it manually. R will do it for you. So the key function that we use for multiple test correction in R is p-adjust. So p.adjust takes in multiple arguments. So it takes on board multiple different things. It takes in a vector of the p-value of interest. So if you're writing code, you can add each of your p-values as it merges to a vector, and then supply that to p.adjust at the end and check which ones corresponds to which. There's a bunch of different false positive correction methods available. Benjamini-Hochberg BH is probably the best one if you're unclear. So that's why in the function itself, we write in method equals BH to say that we're using that one. We've given our vector of p-values, and we also can tell it length, the number of p-values that are present. So if we have, let's say, 100 ones there, that's effectively what we're doing there. And we might have our vector here at the start with 100 p-values. So that means it will return back 100 corrected p-values. And in the demonstration video, you look at how actually that looks, and we can plot these. You can plot the original p-values and the adjusted p-values and see how they're different. So that's one handy function you might want to use when you're coding with R. There are many other packages, and you find out more about them using two key commands. So if we're interested in the package called stats, you can use the package description function to get more info about that package. Another one is to simply ask the help function for information about the stats package. You'll find out in great detail what functions are available in this package, and you can scan through that help code to find example code to help test the functions. At times, it can be difficult to understand what a function actually does until you try it out a few times and try some of the example code and read more about it. So if we do this for the stats package, you'll find things like this. The R version, the last time it was updated, and that's useful for saying if I will use this package or not. If the version of R is maybe 3.6, it's kind of old. It may not be useful anymore. If it was last updated in 1998, it's probably not going to be a good package for you. Likewise, if you use the help function, you'll find out about the functions inside a package and briefly what they do, and often there'll be ones with many, many different functions within a package. In the demonstration video, we'll also talk about how you can make your own functions. So these have a consistent nomenclature of how this is set up. So basically, for a function, what's different, we say a function, we're taking an argument x inside that function. We have curly brackets at the start and curly brackets at the end, which delineate the start and end of the function. So we can call a function 1. So function 1 is not a variable, it's a function. It is called a function because it has that in the start of its name. We can have an argument here. We can have multiple arguments or no arguments. It depends on the nature of the function. We can have many lines of code here or none or very few. It depends on the function. And then return is a code that will send something back to when we call the function. So you have to run this code first, and this sets up the function. So when we call function 1, it will expect an argument in from our code, and then it will return this back. So x is a local variable. It takes in that value during the function, and it's whatever we give it. So if we say value 1 is 33 here, and then we call function 1 with that value 33, 33 will appear here at the start. And then what we'll do is we'll add x is now becomes 33 plus 2, so it becomes now it's 35, and then we return x. So 35 is returned back to the function. So that means 35 is now value 2, and we can print that out right down here. So if we passed 66, we'd return 68, and so on. So that's how a function works. We're calling this function 1 up here. Oh, where are we? There. It's calling it up there. We're giving it this value 1. If you don't give it a value 1, it will crash. Note that. And then we can print out value 2 that we get at the end. Another example of a function is one that takes in 3 arguments, x, y, and z. This is a function with a name. We're going to call it function 2. It's set up similar to before. That has curly brackets at the start, curly brackets at the end. It does some trivial code in there just to give you an indication, and then returns it. So the functions that you call with R are actually built up in the same way. You just can't see them. But the function to calculate the mean, the standard deviation, the median, all work in the same way when you call them. So if we have 3 values, 33, 2, and 3, we can supply these as arguments to our function here and then call it. So now what we're basically doing here is multiplying 33 for x. We're assigning x as 2 by 3 plus 2. So expect to return x and get 8 back when we print our value 4 here. So remember, this function is calling function 2 up here. So we'll go through more examples in the demonstration video. So this is a brief summary of how we can use functions and subroutines to do handy things like multiple test corrections, just for example, how we can get package info to see if packages are useful or not, and how we can create our own subroutines or functions technically in this case because we're passing arguments and so on, how we can create functions within R and do different things with our coding.